Wczorajszy wieczór był snem. Nie wiem skąd wzięła się czarna pieczątka na ręce.
Cały dzień, żeby miło spędzić noc, żeby życie było snem, żeby słyszeć życia dźwięk. Tańcowałem całą noc, żeby życie miało wdzięk. Łykam bas, niby tlen, żeby życie miało sens. Pracowałem cały dzień, żeby miło spędzić noc.
Hey everybody. All right, so I'm recording the first 2 minutes because I forgot to press record in class. So let's do it. I'm going to share the screen and see how it goes. All right, so today we're going to be talking about sorting. And of course, me from earlier today is going to actually do the lecture. But to introduce the topic, the big picture here is we're going to go deeper into Quicksort. I think Quicksort's a really lovely algorithm for reasons that will be described further. And so before we get into this Quicksort algorithm and talk about this topic of avoiding the worst case n-squared behavior, I'd like to remind you of what Quicksort does. So recall that Quicksort is an algorithm that's about sorting a single item at a time. That is, for example, I will pick a pivot, maybe the leftmost item. That's the algorithm I have here that we'll talk about variants later. And when we partition on that pivot, the idea is we get it in place. Okay, so what do I mean by that? Well, all the red items here are less than the pivot. And all these blue items, only one in this case, is greater than the pivot. And if I had any other equal items to pivot, like other 32s, they would be white. So what the partitioning process does is it moves all the red items to the left, puts white in its place, and the blue item over here ends up being bigger, okay, or on the right. Good. Now, there's no specific ordering that these left items end up in. Any partitioning is valid, meaning it doesn't matter what permutation you have of the red items, all of them are equally valid for the purposes of partitioning. Okay, so that's a review of Quicksort. And so now I'll kick it over to me from earlier today. So let's talk about Quicksort and how we need to be careful in order to avoid it behaving badly. In particular, we showed that the runtime's in log n in the best case, where the pivot always lands where? The middle, right? And it's n squared in the worst case, which happens when a pivot either ends up at the very front or the very back or within a constant distance. And then it was n log n in the average case, just like random arbitrary data. Okay. So I asked this question last time, which is, what are some things we could do to avoid worst case behavior? And how'd you guys think about this a little bit? And so I'm just going to spoil a bunch of different philosophies for this, of how you can deal with the problem of avoiding worst case behavior. In other words, how do you keep it so the pivot doesn't just land at the front? That's another way of thinking about it. Okay. So there's roughly 4-ish philosophies for this. The first is randomness, which is to pick a random pivot. So if you pick a random pivot, it's equivalent to sorting arbitrary data, because it's like the structure doesn't matter. You're picking each time a random pivot, should be fine. Someone else mentioned last class the alternate approach, which is just as good, which is to shuffle before sorting. In the shuffling approach, you just literally take the array and shuffle, and there's some algorithm to do that in constant time. And you'll also be in good shape. So as long as you take your problem and shuffle it with extremely high probability, it's going to be n log n. Another approach would be smarter pivot selection. Someone else recommended this as well. Instead of just always taking the leftmost item, pick something else. Third is an introspection, which is the sort is watching its own recursion depth. And if it realizes it's gone really deep, it realizes, this is a worst case input, and then you switch sorts. You could do that. And then the other one is you could pre-process the array and say, like, do some kind of analysis to say, is this a bad array for Quicksort? And if so, don't use it. This approach is philosophically possible, but nobody does this because the first 3 approaches work just fine. Okay. All right. So let's talk about randomness. So this is my preferred approach. I think randomness is the way to make Quicksort really good, even though it does make it a weird algorithm. But randomized algorithms actually are a wonderful thing. A lot of very hard problems in computation, there's no good solution that works in general, but there does exist a randomized algorithm that maybe doesn't get the best answer, but gets you a pretty good answer. That's kind of like, you'll learn about this if you take 1.7. The idea is that if the pivot always lands somewhere good, then Quicksort will be n log n, but there are these rare n squared cases. So for example, if someone gives me an array that's already in sorted order or in reverse order, or the arrays are all duplicates, the Quicksort we described in the previous lecture will have problems. As we saw, the pivot will always end up in the same place. Okay. So there are different ways to deal with bad ordering that involve randomness. The first is to pick the pivots randomly, which will work. And the other is to shuffle before you sort. And both those approaches are basically equivalent. Like they're not exactly the same algorithm, but you get basically the same result. Okay. And so the second strategy, one thing you have to be careful about is when you write your partitioning code, you still need to avoid n-squared behavior. So there's another type of partitioning strategy out there that I won't describe in this class, but it's a common mistake in Quicksort code to get stuck on all duplicates, where imagine you have an array of all 8s, and you do some kind of partitioning strategy where you shuffle it, you have a bunch of 8s. If your partitioning strategy leaves the 8 in that spot and then does another subproblem that's the same size, -1, it's going to be n-squared. So there's a little bit of like subtlety here. Don't really want to go into it in too much detail. Point being, other than this corner case of all duplicates or almost all duplicates, shuffling will work pretty well. Cool. So what I like about Quicksort, one thing I think that's really nice about it is it is so fast, but it's only, or the best version of it is also random. And so this is, I don't like that quote. So I think of Quicksort as this guy. Okay, this is the show Renegade. Has anybody ever seen Renegade, the show? I've had one person out of maybe like 2,000-3,000 people who've seen this lecture have ever seen it. So I've never seen the show. It's from the 80s. It's about an outlaw cop who was framed for a crime he didn't commit. You know, you can kind of get the attitude from the picture. And so Quicksort to me is kind of has that devil may care attitude. Like Quicksort doesn't live by the rules. You know, it's just doing whatever. It's getting unfair labor practice charges filed against him, all kinds of stuff. And you know, he's making it happen, right? And you know, we just live with it. He's a little out of control, but he gets the job done. Okay. Now there's another approach, which is smarter pivot selection. So instead of relying on the wild and woolly long-maned character here, we'll be clever. So in this approach, what we'll do is we'll do some kind of smarter pivot selection. So for example, if you had to, what pivot would you pick? So you got an array of a bunch of items. Which one should you pick? The median, right? So the median would be perfect. We'll talk about that a little. How do you find the median in a little while? You can also approximate the median. So for example, if I give you 3 numbers from an array, 1, 7, and 45, which one should you use? 7, right? Because it's the middle of those 3. It's the median of a small sample. And that's a pretty common approach. Now, for reasons I won't go into here, while this approach seems very clever, it does not work as well as this guy. There's a couple reasons. One, let's suppose you have a pivot selection strategy. For example, pick 3 items, the first, the middle, and the last, and use the medium of those 3. That approach is both deterministic and constant time. It's deterministic because if you pick 3 items, you know exactly what you're going to get back, unlike this guy. And it's also constant time because I'm only using 3 items, right? So any pivot selection procedure where you take a small sample and you are a constant size sample and you do some kind of cleverness with it and deterministically, there is an input that will cause your will cause your array to go to n-squared. So actually that's true of Java. If I do arrays.sort, there are some arrays that will crash arrays.sort. And if you want to, it's kind of a fun side project. You know, if you really, really wanted to, you could probably read this paper and write this up in maybe, I don't know, 3 or 4 hours. If you know, in the summer, you were like, what's the side project I should do? I recommend this. It's a pretty interesting way of looking at, it's a very clever algorithm that it's a black box that uses a special, some clever tricks where it basically doesn't decide what the numbers are. It's kind of like the evil chooser from Project Zero, where it's like an evil chooser for Quicksort, where it doesn't actually pick the values until it really has to. And so in that way, any deterministic constant time sort that is, or Quicksort, can be defeated, and you can construct a bad n-squared input. Okay, so just letting you know. Now, I mean, this could have been its own lecture, honestly, this slide. And I've given the talk before, so if you're curious about it, ask me later. Okay. The other approach would be, okay, I'm just going to trust you, Josh, that if I take a small sample, the first, middle, and last item, and I choose the middle of those or whatever, sure, like McElroy wrote a paper proving that there is a bad adversary. What about if I actually pick the literal median? So if I do that, is it going to work? Well, it says here on the slide it is, but someone give me an argument. If you always pick the median, why could you never go n-squared with Quicksort? Assuming we don't have all duplicates. So you have an array of indistinct items. Why does picking the median every time always give you n-squared? Or n-squared, n log n, sorry. Yeah. You're always dividing exactly in the middle, okay? So you could do this. You could write an exact median quicksort, but in that case, while it is in log n, it would be worse than merge sort in terms of performance. So we'll run the timing test in a little while. Okay. Now this does raise an interesting question, like how do you get the median of an array? What's the algorithm for that? And we'll get to that in a bit. So we got philosophy 1, be random. Just trust this guy. Hopefully it works out fine with extremely high probability, like quantum tunneling level probability, you'll be fine. Strategy 2, take a small sample. Sorry, this is a dangerous adversary. Philosophy 2b is smarter pivot selection just like before, but now pick the actual best one. Now it's too slow. And then 3 is the introspection approach. Now this doesn't really get used in practice, but I do want to raise it as an interesting idea because things like this do happen. This is, for example, in machine learning algorithms. Sometimes you're looking for a minimum of a function and you don't find it, so you'll do a restart. This is kind of a similar idea. So you're just going to watch what's happening. Your algorithm is introspecting on how it's going. And if it exceeds some critical value, like the depth of the tree of calls has gotten more than 10 natural log n, that implies you've gone very far away from a random tree, which should be 2 natural log n or whatever. So in that case, you switch to merge sort and say, someone's given me a bad array. So this works, but people don't usually do it because it turns out that that first approach of being random is usually the best. Now Java, which one does it use based on my storytelling? Everybody catch that? Kind of said a lot of stuff. Yeah? This one, yeah, uses 2a. So Java chose to use 2a. And we'll talk philosophically about why they did that. That's what they used. Okay. All right. So listing all the sorts we have heap sort, we have merge sort, we have merge sort, and then we just talked about quicksort, which is ideally n log n on average, but you got to be careful because there are dangerous situations. And so what we're going to do now is kind of peel back and experiment with some very specific techniques. I gave you some philosophies, but now we're going to see some specific choices. All right. Any questions for you? Continue on. Yeah.
How long does it take to randomize the array?
Randomizing an array could be done in time. Yeah, there's a Knuth shuffle is the canonical algorithm for shuffling an array. Yeah, it's very easy to get wrong so that you have a biased shuffle. But it's a nice algorithm. Yeah, it's like kind of like an insertion sort where each item is given. You can think of it as a random value. Yeah, go ahead.
How do you tell how to
Right. So for introspection, you would need to pass a parameter to your subcall and say, hey, you're +1. And it would just say, okay, I know how many items there are in the array and I've gotten to like too big. Yeah. Or you could use a static variable, but I recommend not doing it or something like that. Or if it's an object-oriented implementation, there's some, I don't know. I'm not sure how we do it. Okay. So let's talk about some different variants of Quicksort. We'll run a couple timing experiments. And so I've said just a couple times that Quicksort's the fastest sorting algorithm. Like it's better than our boring old merge sort. But it's only true if we make the right decisions. And I'm going to model the quick sorting problem as having 3 different choices. There's actually more depending on how you think about Quicksort, but pivot selection is my first. Like how do you decide which pivot? 2 is which partitioning algorithm to use. And 3, what do we do to avoid the worst case? Of those philosophies, philosophy 1, randomness. Philosophy 2, smarter pivot selection, and philosophy 3, the introspection. How do we avoid the worst case? And of course, as I note, it could be covered by the above choices, not necessarily. Okay. So if we run a speed test of merge sort versus quick sort from last time, we'll find out. We're going to do that in a minute. We'll see that it'll have worse performance. So what was the quick sort from last time? I'm going to call it the L3S quick sort. Why that? Well, the pivot selection is I'm always going to use the leftmost item. Okay. Now we already saw that could be dangerous if the array is sorted. We're going to use as our partitioning algorithm. We're going to do 3 scans through the array. We're going to find all the less than items, those are the red ones, and we're going to copy them into our array. Then we're going to find all the white items, that's all the equal ones, copy them in the array. And then we're going to find all the blue items. I guess I could have colored these. Ooh, that would be cool. Anyway, and put those at the end of the array. Okay. And so that approach is going to, if all the items are unique, that white scan will finish in one, just all at once, or just like once. If you have multiple equal items, then they'll all land together. And then what I'm going to do is I'm going to avoid the worst case, this is the last part, I'm going to shuffle to avoid the worst case. And so long as this algorithm will be in log n with extremely high probability, even if you have all duplicates, because of the way the partitioning algorithm works, right? It'll just scan through and copy all the white items, no danger there. Okay, so always use the leftmost pivot, shuffle before you start to avoid the worst case where it's already sorted. And lastly, we're using this partitioning strategy that just copies the items out. Okay, same one from last lecture. So if I run this in IntelliJ, I have here merge sort and I have quicksort, and this is going to be L3S. Okay, that's the classic quicksort from the quicksort lecture. Let me run it, and we'll get back how much. So what it's doing is sorting 10,000 items 1,000 times. So right here during live lecture, merge sort took 1.5 seconds and quicksort took 3. Okay, they did the same job, sorting a bunch of arrays. Quicksort took longer, despite the fact that it's supposed to be faster. And the reason is that this particular strategy, this partitioning algorithm, is slow. Scans through the array 3 times. Okay. All right, so this is what we got. Pretty close to what I got right before lecture. Okay, so I'd say your quicksort didn't do so well. Fine, but not good. Yeah, I'm gonna do one more and then I'll take some questions. Actually, any questions? Because I'm about to launch into a heavy duty thought. Yeah. Could I do one scan? Yeah, I mean, you could, for example, do something where you put like an add first, add last with a single scan. You mean something like that? Like treat the output array as every time you see a small item, put it at the front. Every time you see a blue item, put it at the back kind of situation. You could do something like that. Just not what I did. Yeah, my assumption is we create one destination array. And then we look for all the small items, copy those, look for all the equal items, put those, look at all the blue items, put them at the end. You can optimize into one scan, sure. Yeah. All right. So Tony Hoare, I should mention, his partitioning scheme, going back to just the craziness that this was the first sort he came up with, his partitioning scheme was also fairly complicated. The one you invented during class in the previous lecture, if you got that far while we were talking, was probably relatively simple. Maybe you came up with my idea or something really similar. In his case, Tony did something. I'm actually not going to give his exact scheme because it's like a little confusing to understand, but I'm going to give a very small tweak that I think originally comes from Bob Sedgwick's PhD thesis from the 70s, but it's basically Tony Hoare's idea. You're going to have two pointers that are walking towards each other, and one of them is going to be looking for small thing, or is going to be, it's going to be alerted by things that are not small, and the other one's going to be alerted by things that are not large. It's going to do some swapping. Kind of the idea is looking for inversions. And so we're going to walk those two pointers towards each other, swapping things they don't like. And I'm just going to give you a demo because it'll make more sense if I do. Okay. So here is an array. And in this case, what is the pivot? 17. It's the leftmost item. And so we're going to start, the pivot we're going to assume is at the front, as always. And then we're going to create two pointers, which I'll call L and G. L is going to start just to the left, sorry, just to the right of the pivot, and G is going to start at the right. And their job is to walk towards each other, fixing the problem as they believe. So L, you could think of it as it's a friend to small items. So if it sees something small, great, but it hates large and equal items. G is a friend to large items, right? G likes greater than items, and it hates smaller equal items. And what are they comparing against? How do they have a notion of largeness? The pivot. They care about the relative to the pivot. Okay. So for example, L, it's going to think what about 15? Good. It likes it. G, what does it think about 17? Doesn't like it. Doesn't like equal items. Okay. So what we're going to do is start walking the pointers towards each other. And when they find something they don't like, they're going to stop. And once they both stop, they're going to trade. Okay. Think of them as like bouncers. So here's L. L is okay with 15. So it says, hi, lovely 15. Then L walks here and says, grr, 19. Don't like it. Okay. G immediately, first day on the job, says, I dislike 17. And now L and G are going to, with a practice heave of a bouncer, so, you know, their strength, they've been working out, they're deadlifting, you know, 325, 315, I mean, and they're going to toss these things across. There we go. Boom. So they get time to swap 17 and 19. Okay, good. And then L and G, they know basically at this point, we're happy-ish with what's behind us. Yeah, maybe there's some equal items behind us. And you might say, what's with stopping on equal items? I'll get to that in a bit. Seems like an unnecessary detail, but we'll get there. So at this point, L and G have swapped, and they're going to take a step forward at the same time they throw. And you can think of this as everything over here is less than or equal 15 to the pivot, and everything over here is greater than or equal to. Because that's what L and G are looking. That's sort of the invariant. Okay? Not sort of the invariant. It is the invariant. I encourage you, all of your other professors, listen for how many times they say kind of or sort of, because they're hedging their bets about saying things that are inaccurate. Once you hear it, you can't unhear it. It's really bad. Anyway. All right, here's 32. So what does L think about 32? Don't like it. Okay, immediate trouble. And then what does G think? Also don't like it. Disgusting, exactly. If only I put that. So now we have trouble here too. 17 and 32 trades, so we're going to swap. Where's L going to be after the swap? Where's G going to be? Great, okay, so they swap. L thinks what about 2? Great, okay, 2 is cool. Oh, 26 is grossly large. Okay, great. And then G is going to start walking. It goes left. Okay, 41 is fine, 26 is fine, ends up here. 2 is no good, and also, hey, my buddy. And so at this point, what we've got is everything on the left is less than or equal to, and everything on the right is greater than or equal to. And so once they've crossed, you're done walking. Now, there's a little bit of corner casey stuff here about exactly when they cross, but it's not worth our mental energy. If you had to implement this, you would have to think about it carefully, but I want you to understand the invariant, that basically as L is walking, in its wake, behind it, it only leaves items that are less than, because those are the ones that said were okay. And then maybe it picked up some equal items that G threw at it. And the same thing is true of G. Okay. Any questions about that process, except for one more step? Actually, I'll take questions after this. So is this array here, is it partitioned on 17? I'm hearing some no's and some yeses. Someone who says no, why is it not partitioned on 17? There's one problem still. The 17 itself is not in the right place, right? Where should the pivot go? So if you had, keep in mind, you have 2 markers. There's G and there's L. So if you had to pick, should it go to G or L? G, why G? Because then the 2 should be on the left. If you move 17 here and put it in the L position, who would end up in this spot? 26, that's no good. So what you're gonna do is trade with G. Takes a little thinking to convince yourself that really always works, but it really always works. So G is always going to be on the last of the small items. This is the way I'm thinking about it. Like G is always the last of the small items, and the last of the small items is always a reasonable thing to swap with the pivot. Okay, so what we're going to do is we swap the pivot with G, and there we go. So the old pivot is here, and then we'll have 2 new pivots. Okay, that's Tony Hoare's scheme. It's a little confusing when you first see it. I think if you walk through this demo thinking about the characters and their motivations and like, you know, their backstories and everything, it feels totally fine. And then you're good. But other than that, you know, it is a little confusing. And I should say that Tony Hoare's is even more confusing than this because he just left the pivot in the middle of the array, which makes it's like actually hard to convince yourself that Tony's works. This one I feel good about. Okay, questions about this process? Other than I know that it's like, if I just gave it to you right now, you might have some trouble, but I hope it feels intuitively okay. Yeah.
Not guaranteed that the 17s and pivots all end up in the middle of that.
Right. This is just pure coincidence that the 17s ended up together. Great observation. Yeah. The advantage of this over the three scan process is it only goes through array once. The advantage of it over what someone else kind of has in their mind is this one, because it's doing these big distant swaps, it just turns out that if you work it out compared to other partitioning schemes, it does fewer swaps and less moving stuff around. Yeah. There's another really famous partitioning scheme called, I think it's like Lomuto, that is a little easier to understand than this, but it's not quite as efficient as 1 pointer instead of 2. Yeah. I always like to teach this one because this is the one people seem to like to ask about Java interviews. Yeah.
Does this also run end time?
There's also end time, yeah. And the argument there is you're stepping towards each other. So it's just like L and G are doing that. So if you just count how many times that can happen, it's end. That's the argument. Other questions about this? So when you get practice with this, I think this is your comfort zone. It's like a thing you do a few examples and you feel like, I've understood the, the basic idea. Yeah.
Actually, why do we want to like sort that to like partition generally? Why do we want to do this again?
Why do we want to do this? Great question. So the whole goal of this algorithm when we started is 17. We want to get it into its place. That's the only thing that's supposed to happen. And the way we do that is we make sure that wherever 17 ends up, that all the items to the left of it are less than or equal to, and all the items on the right are greater than or equal to. We don't really care exactly where they land, except that after we're done, the important point is that these items really should all be smaller than or equal to. These should all be greater than or equal to. And we don't care about the relative order, right? We're only, you can think of it as sorting a single item in an array. Make sense? Right. So once we've done that, once I've gotten that one item in place, then I can repeat this process. So if I call this partitioning operation once for every item, you will be sorted. Because it like, so it's interesting to say, what does it mean to sort an array by only one item? That's what partitioning is. You get it in place. Everything else is just like on the right side, the appropriate side, I should say. Yeah. Yeah.
Are there partitioning schemes that account well for duplicate values?
Right. Are there partitioning schemes that account well for duplicate values? Yes. So if, for example, you know you only have k values out of, say you have n values, but there's only k different values like 2, 7, 9, and 12 or whatever. There's only just 4 things. You have a million numbers, but they're always one of those 4. There is a faster partitioning scheme that if you use it for Quicksort, it'll run the whole thing in n time. Yeah. It's a 3-way Quicksort partition, and that's kind of job interview question someone might ask actually. So if I gave you the question, now there's only 4 different items. How do you do partitioning so it's a little faster? That would be the example of a pretty hard algorithm. If you happen to know that you could maybe derive, and if you just happen to know it, and you'd be able to show off your knowledge. And if you don't, then you can maybe work it out on the spot or not. Yeah. What is, I don't have enough time, but yeah, if you want, I can tell you right after. Yeah. Yeah. I taught that one at Princeton because they're 80-minute lectures. And also, but it drags a little to talk about more partitioning schemes. All right, cool. So this partitioning scheme yields a very fast Quicksort. There's faster versions. I'll tell you about one of those in a bit, but the overall runtime still really depends on the way you pick your pivot. Okay. All right. So what this algorithm does, if I run it, actually I just spoiled it. If I go down here and I say Quicksort, oops, nope, Quicksort, Tony Hoare style, LTHS. I'll tell you what that means in a second. This version, here we get, you're not get to see it, but it finishes in 0.94 seconds. So let's give a round of applause to Tony Hoare. Thank you. Thank you, Tony. All right. Okay. So that version is pretty good. All right. So if we use this, we get a faster Quicksort, and there are better ones. So for example, there was on a Java forum, actually, interestingly, not that this is a Java algorithm, but there was a post in September 2011 where someone said, "Hi, I have a new dual pivot Quicksort idea. I think it should be in Java." This is where this Quicksort became popular, and wrote about it, and ran a bunch of tests, and like basically submitted it as like a improvement request for Java. And then sure enough, it was faster, and like this is a better Quicksort than the one everybody was using, not just Java, which is sort of a funny story. There's the whole John Bentley, who's one of the main like big algorithms guys of the 90s and 2000s in the Java world. He was, and also worked with Bob Sedgwick. He was a little astonished by this. He was like, "What? Like some random guy on a forum like invented this new better Quicksort?" And then it opened up kind of a line of research, and people have considered all kinds of other weird Quicksorts. So I actually don't know that this particular one is the current one in Java anymore, but it blew open the door on minor improvements. Okay. So you too could be the like tinkering Yahoo in your basement who comes up with your own Quicksort schemes. Yeah. They're all in log-n. So every single one of these algorithms is in log-n. They're just better constant coefficients. Yeah. Yep. All right. Okay. So what if we don't want randomness? Why might we not want randomness in Quicksort? Like I said first, I said you had to shuffle. So what's bad about randomness in your Quicksort? Yeah.
Assuming the array is random at the beginning, there's just as much chance of it being bad before randomizing it than bad afterwards.
So there's a chance it's bad. That's true, but the chance is extremely small. So I would say that for practical purposes, that's actually not the main reason, because it's so remote. It's like you would need to be worried about like teleportation of your body through the floor. level of where, yeah. Takes time to randomize. Well, I mean, yeah, but actually after all is said and done, it's faster. So that's not the right answer either. Try again. Yeah.
Yep. And it's already kind of sorted.
If it's already kind of sorted, then it's slow. Okay, I think that's a reasonable answer. And so there's a type of sort called an adaptive sort that will look out for close to random or close to sorted and take care of it, but it's not the main reason. Other thoughts? Yeah. Oh, so if they're if you have equal items, that there's some concern that they'll cross over each other. We'll talk about that property in a bit, not the main reason. I have two reasons in my mind. You haven't found them yet, though. Yeah, I'll give you one. The randomness has to come from somewhere, which is a little weird, right? Like maybe the quicksort, you need to like provide a random seed, or it's just like the randomness is just baked in, it's invisible to the user, kind of weird. And I think the second more serious reason is that it makes it hard to replicate what's going on. So imagine you're like, I don't know, doing a world generator or something in project 3 and you're quick sorting something and something breaks and you want to rerun it. It's just like a little weird that that randomness exists. It makes code replicability tricky. So you have to control, either you have to accept no control over the randomness or you need to seed the randomness. And both of those things are sort of strange. Okay. So here's a question for you. Let's try the other approach. Philosophy 2b, where we find the actual median. Question, how do you find the median of an array? Okay, so give me an algorithm for finding the median of an array, and bonus points if it takes linear time. But anything, like your house is on fire, just try n log n first. So you have n log n time to find the median of an array. How do you do it? Sort the array and then in the middle. Yes, that's the easiest conceptual answer. But of course, that would not be a good way to pick a pivot for quicksort if the first step is sort the array, right? Okay, good. All right. So I think this is a perfectly reasonable approach, is to sort the array, pick the middle item in general, but not for this purpose. What if you want to do it even faster? Like, how could you do median in some smarter way? Well, this actually was an open question for a short time. Could it be done in linear time? And so in 1972, there was a paper called, the algorithm is just called BFPRT these days. They called it PIC, but it's been renamed after its authors. And this paper is insane, like the names on this paper. So all these people are incredibly famous. Bob Targin, actually, interestingly. So when I was at Princeton, we had this fun thing where faculty would rotate through as TAs for the classes because their faculty to student ratio is not nearly as low as it is here. Because at Princeton didn't accept literally every human being on earth to take CS. So as a result, I had Bob Targin as my TA for my data structures class once, and that was pretty fun. So he also wrote this paper and invented like a ton of graph theory things. And in fall 2013, when I accidentally wrote the hardest exam problem I ever wrote, only Bob could figure it out, and Bob graded all the answers because he had the expertise to try and read the student's answer. So anyway, I'll tell you about that problem. It was find the second shortest path in a tree. And I forgot to omit, there was some detail I omitted. So yeah. Thank you, Bob. Yeah, of this paper, 4 of the people in it have won Turing Award. So they did this together. That's pretty cool. Anyway, so this algorithm, I'm not going to describe it. I'm sure there's some very nice 3 brown, 1 blue video about it somewhere or something like. But I want to mention that you can use this as a subroutine in Quicksort. You could say, I'm going to use the pick algorithm or BFPRT, and I'm going to use that to pick the median and see how it does. So let's go. Let's use the state-of-the-art technology for finding the median. Exactly. Well, it's not quite the state-of-the-art, but it's close. So if I run this algorithm, always picking the exact median. Just turns out the overhead of picking the exact median is too high. Still going. 4.78 seconds. Okay. Sorry. Let's all boo Bob Targin. Boo. And I'll send that to Bob. All right. So what we got is 3 different quick starts. We got the leftmost pivot, 3-scan shuffle approach. There's a version we swapped out the partitioning scheme with something like Tony Hoare's and got 0.9 seconds. And then we had, let's use the exact median instead of the leftmost item. And that took 4.9 seconds. Okay. So the cost to compute medians is too high. So we basically need to live with n squared as the worst case if we want practical performance. But the chance of this happening if you use randomness is very slow. Okay. Now I love this. I mean, maybe it seems like a bunch of, gobbledygook, but I think it's so cool that partitioning is about sorting an array by one item. But because of the nature of that process, there's like a million different choices you have to make. There's this pivot selection strategy, the partition algorithm, the worst case avoidance. It's like kind of a fun problem to figure out what's up. And yes, of course, people have tried a million different other approaches for all these things. And people come up with different trade-offs in different circumstances. Any questions before I close out this quick sort? Hopefully I've convinced you it's cool. All right, Quicksort I give an extra day to than other algorithms in this class. I just think it's so cool. Yeah.
Could we technically make it faster by just taking a strategy and just like setting some other breakpoint error?
Right. So you could do something like just like cross your fingers, like introspection would be an example. Introspection sort, something like that. Oh, that's a good question. So if you don't shuffle and do introspection sort instead, I wonder what happens. I bet it's a little faster, except for the version where you switch to merge sort, of course. Yeah. Cool. All right. Let's talk a little bit about quick select, which is an alternate median finding algorithm, just as like a little dessert of our day. So I'll tell you that partitioning is a general operation that could be used for other things. Okay, so the selection problem is what we had before. I have an array and I want to find some item that satisfies like it's the fourth quartile or the median or whatever. This problem is a generally useful thing. An example of why that problem is useful is I want to find the median of an array. That would give us a safe quicksort. Okay. Now, as we saw, the algorithm where you use the best exact median algorithm is too slow. But actually, kind of turning things on their head, turns out Bob Targin and everybody's median finding algorithm isn't the best one. Curiously, and this is the part it's going to kind of feel a little like meta or something, but turns out partitioning is the best way to find the median that's known. Okay. And that so how would that work? Let's get a sense. Okay, so this is sort of a whoa, because you use partitioning would be the best way to find the median, which would be the best way to know which items to pivot around using partitioning to sort. Okay, that's my second Keanu of the semester, and I think the last. Okay, so here's the idea. This is the intuition. I want to find the median of this array, so I'm going to partition around 9, and let's say it ends up there. How do I know that's not the median? Because there's more items on the right than the left. It's not in the middle. So what should we do next? You could go back and try again, but I think we've actually saved ourselves some work. I think that we could start over. So could the median be over here? No. So what should we do? Just partition the other side on some arbitrary item. I'll use the leftmost. Okay, so we know the left problem cannot contain the median, so we're going to partition the right. So we'll pick, I don't know, 550. If 550 ends up there, that is also not the median. The median needs to be in this column. Once it gets there, we're good. Okay, could either of these things be the median? No. So what should we do now? Yeah, I'll pick 14 and ends up in the middle. We're good. Okay, simple algorithm action. And that's the fastest known median selection algorithm. Is it as mathematically beautiful as BFPRT with 4 Turing Award winners? No. Is it faster? Yes. There you go. What is the worst case runtime of this algorithm? What do you think? The worst case. So imagine the arrays in order. N squared. The worst case would be the first item doesn't move, then the second item doesn't move, then the third one doesn't move until you get to the middle. So I guess it'd be n over 2 squared, which is still n squared. Okay. All right, so we're done. Okay, yeah. All right. Oh, I already asked the question on the slide. So anyway. So basically, we could get n squared behavior. So just like its cousin quicksort, this algorithm known as quick select also has the Achilles heel that it could be n squared if you're not careful. Okay. How do you avoid this problem? Shuffle. Great. Okay. We could repeat similar thoughts. Or we could use exact median selection. If we use that, we'll get it on the first try. All right. Anyway. Okay, so why does this work on average pretty well? Well, here's the argument. I'm just going to give you a sense of why quick select on average isn't n log n, but actually just n. And here's the intuitive picture. It's not a proof, but the idea is I pick a random item, it ends up somewhere. And I'm going to throw away some amount of the array. And then I'm going to pick another item, and it's going to end up, I don't know, roughly-ish, not quite the middle, somewhere, and so forth. And we're going to keep moving it along, okay? And the point is that, like, obviously, if we get it exactly right the first time, that's why this is a very crude argument. If we get it exactly right the first time, we're done. But you know, let's say we're roughly cutting the array in half as a kind of very vague proof. We would do n compares the first time, n over 2 the second, n over 4 the third time, and so forth. And so if you add n plus n over 2 plus n over 4, and so forth, you'll end up with just n. Okay, this is not a full proof. And probably you feel a little discomfort with the fact that, of course, if I land exactly in the middle, we're done. But on average, you'll end up about halfway-ish. You know, maybe this one's 3/4 along the way, but then the next time it's, I don't know, somewhere more to the middle. And this is not a full proof. It's just giving you a sense. It's a little unkind of me, but I hope that you feel it. Okay. So we could actually use, so we could, in theory, think, okay, if this is an algorithm for finding the median that is even faster, I'll show you on this previous slide. If this gives us something that's even faster than Bob Tarjan and so forth's algorithm, could we use that, right? Could we use quick select to find the exact median? Technically, you could, but it'd be very weird, right? Like you'd be doing a bunch of partitions to find the median, and then you would use that as the item to partition around. You could technically do it. I'm not going to run the experiment. It does actually make logical sense. It's just a weird thing, and it's still quite slow. Okay. What I really want you to get out of this, I mean, this is kind of an aside. What I really want you to get out of this is that partitioning is a general strategy that could in principle be used for many problems, not just sorting, but also selection. And also fun that you can understand the algorithm. Even if I can't prove to you in the 2 minutes I gave you, I can't prove to you that it's really linear on average. Hopefully it feels clearly correct, and it seems plausible that it's fast. Okay, any questions about this? This is the slide I really care about. Other stuff was kind of aggressive. Yeah.
I guess like I just basically it means the worst case scenario, the limit doesn't run faster, but generally
In the worst case, which runs faster? Oh, the deterministic one? The Bob Tarjan version of this? So the Bob Tarjan version of this for an average case will be much slower than this one. But if you got really unlucky, this one would be slow. Yeah. Because this one could run into the situation where it's n squared. Maybe a better picture of the n squared. Okay. So to talk about one more thing that's not quick sorting, which is sorting stability. And this is an idea that someone else brought up earlier. This idea, one of the downsides of shuffle. Okay. So again, we have a bunch of different sorts. We had heap sort, which is sort of like fancy selection sort if you want. We had insertion sort, we had merge sort, we had quick sort. And I'll talk more about sorting summary in a little while. But what I want to point out is a useful feature of sorts you might have seen before somewhere, which is this idea that a sort is stable if equal items are preserved. And by equal, I guess I mean equivalent, like the less than operation considers them equal. So for example, let's suppose we sort a bunch of students by their name, okay? So this right here, you can see that they're sorted, right? We have Boss and Jana, and Lara, and so forth, random names. And then we have their section numbers, okay? In a stable sort, whenever you sort first by name, then by section, the names that are all together, so Boss, Jana, Joni, Rosella, these 4 names are all clustered, like they don't cross back over. They're still sorted by name. Okay. What's the alternative would be, well, it's possible that that second sort is not stable. That is, these 3, Boss, Jana, and Joni, Rosella, who are all in section 3, end up being more or less randomly shuffled around. Okay. You've used stable sorting maybe, like in a spreadsheet. I don't know if you've ever done this, but in Google Sheets, you could say sort by some column and sort by the other column. And then you end up with something like this, where you have everybody sorted first by section as the most important thing, and then by name as the secondary thing. So the idea of stability, hopefully clear. Okay, this is unstable, this is stable. Okay. So in addition to speed, another important property is whether or not it is stable. Okay. So for example, insertion sort. Question for you, since I've been talking so much today. Do you think insertion sort is stable? I got a yell key for you, and I'll give you here a minute to think about it. Think, what does it mean for a sort in terms of its mechanics? And if you want to have a bonus question about Quicksort. Oh yeah, sorry, if you don't remember how this works, so you're repuzzling it out, sorry.
Sorry, no,
All right, I'm gonna spoil it. So insertion sort is stable. And the reason is, good snap, is that when an item that's equal to another encounters its friend, like E, for example, when E starts walking, you can't quite see it here, maybe I got in here. When E starts walking, it's going to, this E, when it travels, it is not going to walk past its other E. You don't swap E's. Once E sees an item that's equal to it, it says, I don't need to walk further. And for that reason, it's stable because any equal item will never cross over. Okay, Quicksort, is it stable? Well, partitioning strategy, if we do the 3 array style and we don't shuffle beforehand, it will be stable. If we use Hoare partitioning, it won't be. So items can end up crossing that are equal. Okay. And of course, if you shuffle, then sure, it's not going to be stable. Yeah.
What's the terminology stable?
Why is it called stable and unstable? It's whether or not it preserves, I guess, the relative stability of equal items. How about that? Yeah. Yeah. Like, I think this is the picture. That's stable. That's not stable. That's why. Okay, cool. So for every sort, you could work out a similar problem to the one we just did, like insertion sort. Hopefully you convince yourself maybe that it's stable, or maybe not. So you can repeat that same exercise for heap sort, merge sort, quicksort. They use the shuffling and see that insertion sort is yes, merge sort is yes, heap sorts no, quicksorts no. I'm not going to cover them though. It would be quite boring to hear me explain exactly why every sort is stable or not stable. All right. Question. Then I'm going to leave you to think about I'll make sure it's in the book. I don't want to spoil this. Maybe I will later. But arrays.sort, interestingly, there's sort object that takes objects, and there's sort int that takes ints. Turns out that sort with objects is merge sort, and sort of integers is quicksort. Okay. So a fun question for you to think about with your friends after is, why on earth did they do that? Okay. All right. So last thing I want to do, and I couldn't get the microphone working before class, is I want to point out that there's a lot of cool resources out there to understand sorting. And this is one of my favorite things out there is these sound of sorting videos. They give an audio visual picture of how sorts behave. So I'm going to show you a few of these and we'll see how it goes. Okay. It's worth your time. I know it seems fun to go outside, but this is more fun. Okay. Oh, we got to watch the video. No, I'm not going to do that. We can get free advice. Yeah. Okay. Sound. Oh, no. People are not, they don't have buy-in. They don't believe in the sounds. Oh, wait, what? Oh, yeah. Yeah, oh, yeah, sorry, sound. Okay, one sec, everybody. Sounds like we might have to do this later because people are really itchy to get out of here with all that. It's on the bottom right. Thank you. I'm not a Macintosh man. This thing? Oh, my gosh. Thank you, everybody. Okay. Let's play through my speakers because it's not playing in the world. So I'm going to play it on my laptop and we'll see. Sorry, you might not be able to hear it on the internet. Okay, here we go. No, curse this earth. I spent 5 minutes. Okay, hold on. We're going to try one more thing. You know what I'm going to do if I don't get it, though, is let you go and then we'll do it next time. But hold on, let me try. What if I can do it? No. Curse the earth. All right, well, anyway. All right, I'm going to do this next time and we'll enjoy it then. So I'll see you Wednesday. Those who are getting up early, you had the right idea. You saved yourself 45 seconds. I have office hours like normal today at 2 o'clock. No bargaining. That's a 3 today.
Question on
Yeah.
is